All right, first of all, we're going to consider motion in one dimension. Later on in future videos, after we get motion in one dimension down, we'll look at motion in two dimensions. So we're going to start with the following properties. We're only considered with straight line motion only. Horizontal motion, vertical motion, or slanted motion, just forward and back or up and down. Second, we understand that forces cause motion, but right now we're only considering the motion itself and changes in motion, which is speeding up and slowing down. And third, the moving object is either a particle or behaves like a particle. We're not going to consider rolling motion, and each part of the object moves together. All right, so first we'll develop what are called the kinematic equations. Kinematic refers to descriptions of motion. So the equations we develop will help us to describe the motion. All right, we'll start by defining displacement. That's delta x, where delta, of course, means change. So our displacement is just simply our change in position. X represents our position at some later time, and x with the 0 subscript, read as x naught, is our position at t equals 0, where we're starting. So our displacement, delta x, equals x minus x naught. Now notice that our displacement has a direction associated with it. So displacement is actually a vector quantity. It has a spatial direction. Now, since we're just doing one dimension, we'll just use plus or minus. And so in our problems, we'll consider one direction is positive and the opposite direction is negative. So displacement can be positive or negative. Next, we'll talk about velocity. And first we'll define average velocity. So V average equals displacement over the time to make the displacement. So that's delta x over delta t. So delta x, the displacement, of course, is x minus x naught. And in the denominator, we have the delta t, which is our later time, minus time equals 0. So we don't write the 0 in. We just have the displacement over t. And the acceleration is how fast our velocity changes. So we define average velocity as the change in velocity over the time to make the change, or v minus v naught over t, where again, v naught is our velocity at t equals 0. So instantaneous velocity, how fast we're going right this instant, I take the limit as delta t goes to 0 of displacement over time, delta x over delta t, and that gives me dx dt, the derivative of position with respect to time. Average acceleration is change in velocity over change in time, delta v over delta t, or v minus v naught over t. And then the instantaneous acceleration, we take the limit as delta t goes to 0 of delta v over delta t, and we get dv dt, the derivative of velocity with respect to time, which is the same as the second derivative of position with respect to time. If we have constant acceleration, then our average acceleration is equal to our instantaneous acceleration. And then in that case, we can develop a constant acceleration equations for our position and velocity as functions of time. So I take a equals v minus v naught over t, solve for v, and we get v as a function of time equals v naught plus at. So now we have velocity as a function of time for constant acceleration. Now looking at this equation, we see the two terms v naught and the at. The v naught is my initial velocity at t equals 0, and then the at is how my velocity changes in time. So that's how much my velocity has changed from the initial because of the acceleration. So a times t, of course, gives me velocity. Acceleration is in meters per second squared times time in seconds. I end up with meters over second, which is a velocity. All right, now for my average velocity equals x minus x naught over t. Multiply both sides by t. I get x as a function of time equals x naught plus v average t. Now that always works even when you have an acceleration. So that equation, x equals x naught plus v average t, will always work even if we have an acceleration. But we have to be careful that we use average velocity. So now if my acceleration is constant, then my x equals x naught plus v average t, I can replace the v average with the average of my initial and final velocities. So v plus v naught divided by 2. I put that in for my average velocity. I multiply the half through and the t through the parentheses there, combine the terms, and I get x naught plus v naught t plus 1/2 at squared, the equation at the bottom in the box. So make sure you understand the algebra step by step there. So now we have an equation that gives our position as a function of time for constant acceleration. So now we have two equations that we can use to solve all of our motion problems. All right, so here's our constant acceleration kinematic equations for position and velocity. X as a function of time equals x naught plus v naught t plus 1/2 at squared. V as a function of time equals v naught plus at. So these two kinematic equations can be used to solve all of the one-dimensional motion problems when we have constant acceleration. All right, look at the position as a function of time equation on the right side. The x naught, that's where we start. That's our initial position. The v naught t shows how much our position changes due to our initial velocity, and the 1/2 at squared shows how much our position changes because of the acceleration. So we have the three terms: initial position, how much our position changes because of our initial velocity, and how much our position changes because of the acceleration that we have. All right, so again, I've been using this word kinematic. Kinematic refers to descriptions of motion. All right, now we derive those kinematic equations directly from the definitions of displacement, velocity, and acceleration. Now here's another way we can derive the kinematic equations for constant acceleration using calculus. So I start with constant acceleration. So my average acceleration is equal to just a, because it's constant, it's not changing. Then I write that a is dv dt. We know that the acceleration is the derivative of velocity with respect to time. So if a is dv dt, then I know that a dt equals dv, and I can integrate between t equals 0 and some later time t. So the integral of a dt gives me at, and the integral of dv just gives me v. But now I need my limits are going to be in the velocity at t equals 0 and the velocity at later time, which we just write as v. So the integral on the left side gives me at. The integral on the right side gives me v minus v naught. Now I solve for v, and I get v equals v naught plus at. Same equation we had before. So we just start with the acceleration is a constant a, and we know that's dv dt, and then we integrate that from from 0 to t, and v naught to some later time velocity v, and we get our velocity as a function of time. All right, knowing that velocity is the derivative of position with respect to time, or dx dt, now we can integrate the velocity. So the integral of v dt equals the integral of dx, and the limits in the integration, we're going to go from 0 to t, and for the limits on the dx integral is our position at t equals 0 and our position at time t. So when I integrate those, when I integrate v, I get v naught I have to replace the v, since v is a function of time. So I can't just integrate and get vt, because v is a function of time. So I have to replace the v with the velocity as a function of time, which we got in the previous slide. So that's v naught plus at. So the quantity v naught plus at dt is the integral on the left side. And on the right, I just have the integral of dx. All right, so when I integrate with respect to time, I get v naught t plus 1/2 at squared. My limits are 0 and t, so when I put the 0 in for the t's, of course, I just get 0. So that's the result, v naught t plus 1/2 at squared. On the right side, I just get x minus x naught when I do that integral. Now I solve for x, and I get x as a function of time equal to x naught plus v naught t plus 1/2 at squared. So again, we can derive the position as a function of time equation by integrating the velocity. So this just shows an alternate method for deriving the kinematic equations. So now that you know how to derive the kinematic equations, you shouldn't have any trouble remembering these equations. You shouldn't have to go and look them up. You know how to derive them. And once you understand all the terms in the equations, it's very easy to remember them. Now sometimes when you're solving problems, you'll get a problem where they don't give you the time. So in that case, we can eliminate the time from the two kinematic equations. So if I start with v equals v naught plus at and x minus x naught equals v average t, and v average equals 1/2 the quantity v plus v naught. So I'm going to start with those. Now, in the second equation, I solve for t. I get x minus x naught over v average, and I put that in the replace the t in the first equation with that expression for t, and I get v minus v naught equals a times that quantity, x minus x naught over 1/2 v plus v naught. And I do a little algebra, and we end up with the equation at the bottom. So I'm not going to read through each step. You can read through the algebraic steps there. But the result is the equation at the very bottom. V squared equals v naught squared plus 2a delta x, where delta x, of course, is the displacement. A is our constant acceleration. So now we have a third equation. Now this third equation is not independent of the other two. All we did was we took our position as a function of time and velocity as a function of time, eliminated the time between the two. So you take one equation, solve for t, plug it into the other one, do the algebra, and you end up with the equation at the bottom. So v squared equals v naught squared plus 2a delta x. So this third equation is very useful for solving problems when you're not given the time. Now, it's not necessary to use this equation. As I said earlier, our position as a function of time and velocity as a function of time, those two equations can solve all of our one-dimensional motion problems. It's just that when you're given a problem that doesn't have the time in it, you have to do an extra step, because first you have to solve for the time, and then you have to do another step to find the unknown quantities. So you may have to do an extra step, but that's all. You can still solve all the 1D motion problems with the two original kinematic equations. Position as a function of time and velocity as a function of time. This third equation here, the v squared equals v naught squared plus 2a delta x, that's just another equation that we can use that will eliminate an extra step in problems where we're not given the time. All right, summarizing, here are our three kinematic equations. The first one, velocity as a function of time, is our initial velocity v naught plus acceleration times time. The second one is our position as a function of time equals x naught, or the initial position, plus v naught t, where v naught is the initial velocity, plus 1/2 at squared. All right, those first two equations, these are our constant acceleration kinematic equations. The third equation, v squared equals v naught squared plus 2a delta x, we get that equation by eliminating the time between the first two equations. So that third equation is useful for solving problems where we're not given the time. But we can solve all the one-dimensional constant acceleration problems by using the first two equations. But if we're not given the time, it just takes an extra step. So the third equation helps us to eliminate that step in problems where we're not given the time. But it's not necessary to use that equation, but it will just save us a step in the problem solving. Okay, so that's the end of this video. So future videos, we'll look at some problems where we apply these equations. Hi, Dr. C here. I want to ask you to please help support this channel. There are links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, I receive a small commission to help produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions. Thank you for supporting this channel, and I hope you find it useful.